Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back, my students, and today we are talking about Newton's laws of motion. Okay, so with Newton's laws of motion, we're going to be discussing the three laws of motion. We're going to be discussing the application and how you've been using them every day without even realizing. So let's have a look. Um, Okay, so objects don't start or stop on their own. So the first law of motion, simply speaking, is the law of laziness, the law of inertia. And simply put, it's basically all it's stating is that objects don't like you changing what they're doing. So objects will keep doing what they're doing. So if an object is stationary, it will remain stationary. If an object is moving, it will continue moving at constant speed. Um, and that's basically it. So if you think about an object in outer space with no external forces acting on it, no air resistance, nothing like that, that object, if you throw it, say for example an orange, and you throw it in outer space, it will continue moving at constant speed and it will never ever stop in theory. Um, and so, likewise, an object that is standing still, that is not moving, will not experience any change, assuming there is no external forces acting on it, and will remain stationary, will remain in its position. So that is basically Newton's first law. So Newton's first law is the law of inertia. Objects, objects, I'm just going to summarize it. Objects don't like to change what they are doing. And that's really the simplest way I could put it. Okay? So an object that is moving at constant velocity will continue to move at the same speed and the same direction as long as no net force is acting on it. Now there might be some forces acting on it, but as long as they are equal, as long as there's no net force, as long as they cancel each other out, as long as they counter each other, then it's fine. And we'll come to discuss that as well in a minute. Okay, so here we have an example, and it's a very interesting example. We have, it looks like an anvil, and basically it's hanging from a hook. And you're being asked a question, what would happen if you jerk it? If you jerk the lower string downwards rapidly? Okay, so basically, if you jerk that string down rapidly, it's going to yield a different result than if you were to do it slowly. Why is that? Well, back to the law of motion, the first law of motion, which state that an object that is at rest would want to remain at rest, and an object that is moving would want to continue moving. So let's think about that for a moment, and let's think what would happen if you jerk it down quickly. So if you were to jerk the lower string down rapidly, okay, just go very fast, then this anvil here wouldn't want to move. Okay, so if you pull down on that string really quickly, that anvil wouldn't want to move. And so therefore, what's going to happen? It's very heavy. That line is going to be cut over here. So the lower line, the lower string would break. However, if you do it slowly, if you do it really slowly, okay, and give that anvil some time to react, then what's going to happen is the top line or the top string is going to break. And the reason, once again, is because so once it continues moving, it doesn't want to stop. Okay, very good. So that, once again, is just a simple demonstration of the first law of motion. Is that basically if you move that string down very quickly, this anvil would want to remain still, and therefore that lower string would break. Let's look at the second law of motion, and the second law of motion simply states that you basically have those variables that affect the forces, and those are the variables. So combining the preceding results We can express the acceleration caused by a single force in the form of an equation, and this equation is simply probably one of the most famous equations in physics, and that is force equals mass times acceleration. Okay, and what that's stating is the force acting on an object is directly related to the mass of the object and the acceleration. Okay, the mass of the object and the acceleration. So let's assume, for example, that there's an object that's quite massive, and it's accelerating at a rapid rate. Then the forces involved are very, very big, and that is sort of like the likes of an asteroid. Okay, what if we have a much smaller object that is moving at a very fast rate, then it also experiences very high forces. And that's the example of that is a bullet, for example. A bullet is very small in mass. A bullet might just be about 0.05 kilograms, about 50 grams, but then it's moving at very, very high acceleration, which causes immensely huge forces. Okay, and that's enough forces to knock down a person. Um, so that's what we're talking about with Newton's second law, is that force equals mass times acceleration. Acceleration is proportional to the force and inversely proportional to the mass in this equation as desired. Rearranging the equation yields a form of Newton's second law. So that's basically it. And any form of it. Another way I could express this is a triangle, and I find that quite a few students like this. And so that way, if you want to find the acceleration, for example, then you know that it's force over mass. If you want to find the mass of an object, well, if you know the forces acting on it and the acceleration that it has experienced, you can actually work out the mass of the object just based on that. Okay, here's an actual example. An 1800 kilogram car. I'm going to try and draw a boring car. Here we go. There's a car and it is experiencing an acceleration of 3.8 meters per second. Now I'm just going to draw this vector over here. 3.8 meters per second squared. It is 1,000, the mass of the car is 1,800 kilograms, and the acceleration is 3.8 meters per second squared. And of course, you're being asked about the forces. You're being asked about the force. So the force is going to be F equals mass times acceleration, which we should be familiar with by now. Force equals mass times acceleration. And so, do we have the mass? Yes, of course we do. It's 1,800. Do we have the acceleration? It's 3.8. And so I can work that out. And that is 1800 times 3.8, and that equals approximately 6,840 newtons. Now the unit for force is newtons, okay? But notice as well that the unit for mass is kilogram and the unit for acceleration is meters per second squared. So really the unit for force can also be kilograms, meters, meters per second squared. Okay, kilograms meters per second squared. That is equivalent to newtons. So rather than writing all of this here, kilograms meters per second squared, we can write newtons. So the answer is approximately 7,000 or 7,000 newtons. Or since we're working with two significant figures, I'm going to go with 6,800 newtons. That's the answer. Okay. Hope that wasn't too hard. Let's move on. Concept check. Is it possible for an object at rest to have one force acting on it? If your answer is yes, provide an example. If your answer is no, explain why not. Okay, that's a very interesting one. Um, it's not really possible for an object that is stationary, that it's not moving, to have only one force acting on it. Because by definition, if it did, then it would start accelerating and no longer remain stationary. However, it is possible for a stationary object to have two forces acting on it. three forces acting on it, four forces acting on it, as long as the net force is zero. Now, how can an object have two forces acting on it and still remain at zero? Well, if one is acting up, one is acting down, then they cancel each other out. If there are four forces that are acting on the object, say for example, four things pulling from every direction, then obviously they cancel each other out as long as they are equal and opposite, and so therefore the overall force acting on the object is going to be zero. Okay, so really simply the answer to the first one uh, is no. But I did have a student ask me what would happen if an object is in flight. Say, for example, you throw an object upwards, right? There is a momentary moment, like there's just a moment at which, if the object is up in the air, as it's doing this parabola, right? At this point here at the top, the object is technically stationary, it's not moving that moment, right? Okay, so here, I'm trying to demonstrate it on camera. If I throw this pen up in the air, it's going to at one stage, it's going to be completely stationary before it starts moving down again. Now, is there a force acting on it? There's always a force of gravity acting on it. So that's the only example I can think of where an object can momentarily, and that means very, for a very, very, very short time, be stationary and have a force acting on it, a single force acting on it, that is gravity. But otherwise, for the majority of the time, we're talking about the vast majority of the time, nearly 100% of the time, no, you can't have one force acting on an object because then it will start accelerating. Okay, let's look at question number two. And question number two asks, you push a 12.3 kilogram shopping cart with a force of 10.1 newtons. What is the acceleration of the cart? Well, let's first and foremost write down the formula that we're all very familiar with. Force equals mass times acceleration. Or if you want to, you can write it this way. Force equals mass times acceleration. What is the acceleration of the cart? Well, simply speaking, acceleration is going to equal force over mass. Force over mass, as we can see from this beautiful triangle over here. Acceleration equals force over mass, which equals 10.1 all over 12.3 kilograms. And of course, that equals approximately 0.8. 10.1 divided by 12.3, 0.82 meters per second squared. Please don't forget your units. That is part A. Let's look at B. If the cart starts from rest, how far does it move in 2.5 seconds? We've gone back to kinematics, haven't we? Right, well, hopefully you still remember your equations. VIT plus half AT squared. That is the equation I'm going to use here. The change in displacement or the change in position, which is x final minus x initial, is equal to the velocity, the initial velocity multiplied by the time, plus half times the acceleration times time squared. Now, since it starts from rest, you should immediately have your alarm bells going off. Rest means zero. So the initial velocity over here, v initial, is going to be zero, and therefore 0 times t is zero. So we can just forget this whole thing in the beginning. So it's just going to be, excuse me, change in position or distance covered is going to be half multiplied by acceleration, which we've worked out over here in the previous question, 0.82 multiplied by time squared. Where do we get the time from? Well, it's in the question itself. The question says, how far does it move in 2.5 seconds? So we're going to multiply it by 2.5 squared, and that should give us the answer, which is 0.5 times 0.82 times 2.5 squared, which equals 2.6 meters. 2.6 meters, which is approximately right. Okay. So once again, we've had to use a kinematics formula there. And it's all linked together. Okay, physics is linked together. So just make sure that you understand the question properly and you know what the variables are. And the reason we didn't use this once again is because the initial velocity is zero, so we can just get rid of all that since it's zero, and we're just left with this over here. Okay, let's move on to the next question. Here we have a metal head of a hammer, which is loose. To tighten it, you drop the hammer down onto a table. Should you drop the hammer with the handle end down, that is the wooden handle, as in case 1, or should you drop the hammer with the head end down, as in case 2? Or does it even matter? Will you get the same result either way? Well, it turns out it does matter. So the funny thing about this situation is, of course, if you drop the hammer, I just happen to have a hammer right here, which is really quite useful. So I've got a hammer right here. Now, obviously, this side of the hammerhead, is very, very heavy, and this side is quite light. It's very light. So if I drop it on its head, okay, if I drop it on its head, this is the joint we're worried about. This is the joint we're concerned with. We want to make this tighter, and for some weird reason, we don't want to just sort of push it together. We just want to do it the fancy way, which is I want to drop the hammer and I want to make it tighten itself. Right, because I can, which is fine. So if I drop it this way, what's pushing down? What's pushing down on this joint? What's pushing down on this joint is the weight of the handle. And the handle is quite light. But if I push it down this way, if I drop it this way, then what's pushing down on here is the weight of the head, which is quite heavy. And that makes a difference. So this is where the reasoning and the discussion comes from. It might seem that since the same hammer hits the same table in either case, there shouldn't be a difference. Actually, there is. In the first case, the handle of the hammer comes to rest when it hits the table, but the head continues downwards until a force acts on it to bring it to rest. The force that acts on it is applied by the handle, which results in the head being wedged more tightly onto the handle. Okay. Since the metal head is heavy, the force wedging it onto the handle is great. In the second case, however, the head of the hammer comes to rest on the table, but the handle continues to move until a force brings it to rest. The handle is lighter than the head, however, thus the force acting on it is smaller, resulting in less tightening. So all it's saying, simply speaking, is that if you drop the hammer on the handle, the head is going to push down with a greater force, making it tighter. So in fact, this case here is going to be the better option to tighten that joint. Let's move on. The second law also applies to net force, and what that means is you can have more than one force, and all you have to do in this case is just add them together. So the total force, sigma, over here just means total. It's just a fancy word for total force. Total force equals mass times acceleration for everything, really. So you take all the forces involved and you can add and subtract them the way you would add and subtract vectors. And we have an example on the next page here. So we've got Mo, Larry, and Curly pushing on a 752 kilogram boat that floats next to a dock. So here's Mo, here's Larry, and here's Curly. And they are all pushing, as you can see, they're down on one knee and they are pushing in the same direction. 1, 2, 3 in the same direction. They're each pushing in the same direction. And the question is, they're pushing with this kind of force here, 80.5 newtons. And the question asks, what is the boat's acceleration if they all push in the same direction? Well, I'm going to try and visualize this. So I'm going to go 1, 2, 3. All of them are pushing with 880.5 newtons each. So that is going to be 80.5. The next one is going to be 80.5. And then last one is going to be 80.5. Meaning they are all pushing with a force of 241.5 newtons. So now that we've got the total force, what is it asking for? What is the boat's acceleration? What is the boat's acceleration? Do we have the mass of the boat? Yes, we do, right up here. The mass is equal to 752. What is that formula again? It's force equals mass times acceleration. What are we after? Once again, we're after the acceleration. So the acceleration is going to be force over mass. So acceleration is equal to force over mass, which equals 241.5 divided by 752 kilograms, which equals 241.5. Looks like it's about 0.3. Divided by 72 equals 0.32 meters per second squared. Okay, hopefully that wasn't too tricky. All we're saying here is that you can actually add the forces. Let's look at part B then. Part B says, what is the boat's acceleration? And I'm going to use a different color just to distinguish that from the other one. How about green? I love green. My favorite color, really. Okay, part B says, what is the boat's acceleration if Larry and Curly push in the opposite direction from Mo? So you can actually see that Larry and Curly in this picture here are pushing in the opposite direction from Mo. So what that means is now we have to worry about signs. So once again, I'm going to draw this diagram. So the first one is pushing with 80.5 newtons. The next one is pushing with negative 80.5 newtons, and that is because where did the negative come from? Well, they're pushing in the opposite direction. So it's going to be negative 80.5 newtons for this guy as well, for Curly. So what is going to be our overall force now? Well, it's quite obvious, isn't it? That cancels with that, and we're left with minus 80.5 newtons. So in fact, the boat is not even moving forward this time around, it's moving backwards. And we're asked to calculate the acceleration once again, which means A is equal to force divided by mass. The mass hasn't changed, has it? The mass hasn't changed, not even a little bit. So what we have to do here is just go minus 80.5 divided by 752, and that should equal, well, funny enough, that is going to be a very small amount of acceleration in the opposite direction, approximately 1.1 or 1.2. It's going to be, oh, sorry, 0.1, negative 0.1. Oh, I don't like this equal sign being so close to the negative. I'm just going to put it over here. Negative 0.11. Oopsie. Negative 0.11 meters per second squared. So I'm having a few problems with my Microsoft pen. Sometimes there's a bit of a delay. Oops, now we've done that. Okay, we've got a follow-up question here in the guided example 5.4, where it talks about Mo, Larry, and Curly. All push to the right with 80. Oh, this time they're pushing to the right with 85 newtons. If the boat has an acceleration of this, then what is the mass of the boat? Okay, so this time it's a slightly different scenario. So we know the acceleration, we know the force, we don't know the mass. Let's draw that triangle, guys. Let's draw that triangle. Force equals mass times acceleration. So far, so good. Okay, and so we have three forces acting on the right. Mo, Larry, and Curly, each of them pushing with 85 newtons this time instead of 80.5. So 85 times 3, and that is going to be 255 newtons. 255 newtons. That is the total force. Sigma force equal 255 newtons. We also have the acceleration this time, which is 0.53 meters per second squared. Now that is a lot of acceleration. That means the boat has probably lost some weight. It was 752 kilograms before. I think it's going to be quite a bit less this time. Anyway, so mass is going to equal force, which is 255, divided by the acceleration, which is 0.530. And that is going to equal the mass, and that is going to be approximately 481 kilograms, which obviously is quite a bit less than 752, which is what we had before. So that is the answer to number 3. Okay. Number 4 says, I'm going to use purple. Number 4 says, what force must be exerted on a 1,500 kilogram car to make it move with the acceleration of 3.8 meters per second squared? So that is the mass, that is the acceleration. We are looking for the force. Force equals mass times acceleration, which is simply 1,500 multiplied by 3.8, and that will equal the force, which is approximately 5.7 or something. 1,500 times 3.8, and that is 5,700 newtons. Okay, very good. Should we do question 5? Let's go, we're on a roll. Now what I'd like you to do is actually try and give question 5 a go. Pause the video, try and do question 5, and then check and see if you got it right, because I'm going to do it right now. Okay, just going to draw that triangle one more time. Force equals mass times acceleration. Let's look at question 5. You pull your little sister on a sled across an icy, nearly frictionless surface when you exert a constant horizontal force of 120 newtons. The sled has an acceleration of 2.5 meters per second, and the sled has a mass of 7.4. What is the mass of your little sister? Ooh. So now we're using a bit of maths to try and work out missing variables. So we just got to use parentheses or brackets. Okay, so we have force equals mass times acceleration. What do we have? We have the mass of the sled, but we don't have the mass of the sister. So that's what we're trying to find out, the mass of the sister. So 7.4, which is the mass of the sled, plus the mass of the sister, which I'm going to write as ms, meaning mass of sister, multiplied by the acceleration, which is 2.5 meters per second squared. That is acceleration. And this here, this whole thing is mass, m. This whole thing is m, but it's missing, obviously, the sister. And that equals 120 newtons. So all we have to do is do some juggling and reshuffling. So the first thing I would do is divide by 2.5. That way I get rid of this 2.5 over here. And so that gives me a nice number, which is 2.5, 48. So 48 equals 7.4 plus mass of sister. Mass of sister is going to be 48 minus 7.4, which is going to be 40.6 kilograms. And that's about right. Okay, and that's how you do that one. Okay, let's have a look and see if we can keep going here. Oh, we're going to Newton's third law. So we've done the first one. Remember, just a quick recap. First law of thermodynamics. First law of Newton's motions. First law of motion is the law of inertia, which is the law of laziness, which is that objects don't like changing what they're doing. If it's moving at constant velocity, then it would like to keep going. Thank you. If it's stationary, then it would like to stay stationary. Second law is that force is equal to the mass multiplied by the acceleration. And now we come to the third law, which is probably one of the most quoted and yet misunderstood laws out there, which is that forces come in pairs, and for every action there is an equal and opposite reaction. Okay, for every action, force acting on an object, there is a reaction. Okay, so here we have a question that talks about two groups of canoeists who meet in the middle of a lake. After a brief visit, a person in canoe 1, so that's this canoe over here, pushes on canoe 2. So this person, in fact, is pushing on canoe 2, gently speaking. with a force of 46 newtons. The mass of canoe 1 and its occupants is 150 kilograms, so that's the mass of this canoe is 150 kilos. Well, the mass of this is equal to 250 kilos, and we are asked to find the acceleration. Um, okay, so over here, I can see from the rest of the example that they've chosen F2 to be 46. So obviously the forces are going to be equal and opposite. So if it's going to be 46 newtons in one side, it's going to be negative 46 newtons in the other side, and that's what third law of motion talks about, how there's an equal and opposite. So if they've chosen this one to be 46 newtons, then that means this one's going to be negative 46 newtons. And of course, let's go back to the triangle. Forces equals mass times acceleration. And what are we trying to find? We're trying to find acceleration, which is quite easy now. All we have to do is divide. So force divided by mass, 46 newtons divided by 250. That is equal to approximately 0.184. So that is going to be 0.18 meters per second squared. So that is going to accelerate over here. Acceleration of approximately 0.18 meters per second squared. Whereas the first one's going to be negative 46 divided by 150, which is going to be, so this is going to accelerate at negative 0.31 meters per second squared. And that's expected because this one's lighter. This one's lighter, and that's kind of expected, isn't it? The lighter one is going to have a bigger acceleration. Okay, let's have a look. Oops, what do we have over here? We have a follow-up. If the mass of canoe 2 is increased, will its acceleration increase, decrease, or stay the same? Calculate the acceleration. Okay, well, so once again, force equals mass times acceleration. And we have 46 newtons equal 25,000 times acceleration. Obviously, it's going to be a lot less now. Because imagine, like, the mass of the object now is so much bigger. So it's so much heavier, so therefore it's going to accelerate very, very slowly. Very, very slowly, in fact. So divided by 25,000, this is going to be 100 times smaller than what it was before. So it's 1.84 times 10 to the power of negative 3 meters per second squared. Okay. Number 7 is a concept check. As you hold a book at rest in your hand, two forces are being exerted on the book. Identify these forces. So obviously the forces are, if you're holding a book in your hand, the first force that's acting is the one acting down, which is the weight. And then there is an upward force, which is reaction force from your hand. So we have weight. Here's the book. We have weight acting downwards, and then we have reaction force acting upwards. But I don't like the way I drew that because they should be equal and opposite. So there it is. We have weight acting downwards and reaction force from your hand acting upwards. What else is the question asking? B. Are these forces equal in magnitude in opposite direction? Well, I just said that before, so yes. Otherwise, let me put it this way. If the reaction force was more, then the book would be going up, okay? Would be going up, so you'd like flicking it upwards. If the weight was more, then your hand wouldn't be able to handle it and it would be going down, okay? So that's why they have to be equal and opposite. If the book is actually perfectly fine, like just sitting like that, then that means the weight is equal to the reaction force. If the weight was more, then my hand would be going down. If the reaction force was more, then it'd be going up. Since they are equal and opposite, the book is stationary. What's C asking for? Are these forces an action-reaction pair? Explain. Are they an action-reaction pair? So first of all, In order for them to be an action-reaction pair, they have to work on two different objects. But since they are working on the same object, um, let me just think about this one for a second. They're both working on the same object, so no, no, because they are working on the same object. So an action-reaction pair by definition is one that is not working on the same object and it's working on two different objects. Question 8 says, a 71 kilogram parent and a 19 kilogram child meet at the center of an ice rink. An ice rink is a place where people go for skating, ice skating. So we've got a 71 kilogram parent and a 19 kilogram child meeting at the center. They place their hands together and push. If the acceleration of the child has a magnitude of 2.6 meters per second squared, what is the magnitude of the parent's acceleration? Excellent question. Lovely. So the first thing I like to do here is I like to draw it. So here's the parent and they are pushing against the child who is much, much smaller. Okay, and they are both on the ice skating rink. So here's the rink and they push outwards against each other. What's going to happen is the kid is 19 kilos while the parent is 71 kilos. And let's go back to, so what do we have here is we have the acceleration of the kid. Acceleration of the kid is 2.6 meters per second squared. We don't have the acceleration of the parent. Okay. So what we know here is that forces are going to be equal and opposite. That's what we know. So the acceleration is not going to be equal and opposite. The mass isn't going to be equal. Obviously, one is 19, one is 71. But the forces are going to be equal and opposite. So what can we do with that? Let's work out the force for the child first. And if we find out the force for the child, we can find out the force for the parent. So 19, force equals mass times acceleration. Remember, mass times acceleration, which means 19 times 2.6, which equals 49.4. Now, funny enough, that's going to be exactly the same over here, except it's going to be opposite. So it's going to be negative 49.4. And now that I know that, negative 49.4 Isawi equals mass times acceleration, which equals 71 times A. And so what I have to do here is negative 49 divided by 71, negative 49.4 divided by 71 Isawi A. And A equals times negative 1 divided by 71, and that equals negative 0.7 meters per second squared. And of course, as far as direction is concerned, it's going to be pointed that way. So yeah, so it's negative already, so which means it's in the opposite direction. Okay, much smaller acceleration because the parent is a lot heavier. That's all. Very good, let's move on. Okay, a few lesson checks here with regards to 5.1. What do we asked? What do we asked here? So we asked, identify what is required to make a resting object move or a moving object change its speed or direction. Remember the law of laziness, the law of inertia. An object will remain at rest. An object will remain moving at constant speed unless acted upon by an external force. So what is required? What is required is a force acting on the object. And just to be a bit more accurate, a non-zero net acting force. And that just means I would like the force acting on it to not be cancelled out by any other forces. So if there are two forces acting on it, all good, as long as one of them is bigger than the other, then the object is moving. But if they are both equal and opposite, then they're going to cancel each other out. So that's what this means. Non-zero means bigger than zero. Net means, so as long as there's a net force and not cancel out. Number 10 says, apply what happens to the acceleration of the object if the net force that acts on it is tripled in magnitude. Simply speaking, the acceleration is going to triple. So let's see if we can prove it mathematically. Force equals mass times acceleration. Let's take any mass of any object. Let's just say 1 kilogram bowling ball. 1 kilogram, here we go, a bowling ball, 1 kg. And let's say the acceleration of it is 1 meter per second. I'm just going to keep it simple. 1 kilogram bowling ball, and the acceleration is 2 meters per second. 2 meters per second. I'm just going to make something slightly different. So the force is going to be 2 newtons, yeah. Now the question says, what if we triple the magnitude of the force? What's going to happen to the acceleration? Let's triple it. Let's, rather than put 2, let's make it 6 newtons. Now the mass stays the same, 1. What's going to happen to the acceleration? It's going to suddenly be 6. So that means this also tripled. It will triple, which is what we started off with. Number 11 says, give an example. Describe a situation in which you exert a force on something but it does not move. Identify the action force and the reaction force, the relative size of these forces, and the objects they act on. So this reminds me of like pushing on a train. Suppose you push a loaded train and it doesn't move. So you might be tempted to say that it doesn't move because the force you exert on the train is equal and opposite to the force the train exerts on you. While this is true by Newton's third law, the two forces cannot cancel each other because they act on different objects. So one is a force on the train, the other is a force on you. The train doesn't move because the force of static friction on the railroad balances out with the force you exert on the actual train. So the two forces cancel because they're equal and opposite, but they're not an action-reaction pair. Okay, so that's, yeah. And the same thing would be true if you were pushing a building. So if you were to push a building, obviously you would exert a force and the building would exert a force back on you. But just because you push a building and it doesn't move doesn't mean the force isn't there. So you might feel like if you push in the building, for example, the building is obviously not going to move because of static friction. It's not it's not sitting on ice, frictionless ice, or a layer of air where it will be able to move, or we're not in outer space, say for example, where there's no friction. It is stuck to the ground and there's a lot of friction there. You cannot overcome that friction so easily. And so, but you do have those action and reaction forces. As you're pushing on the building pushes back on you, and which is why you move back. Okay, question 12. What does question 12 want? Use Newton's laws to explain why a shopping cart remains at rest if you do not push it. Well, we explained that a shopping cart will remain at rest if you don't push it because there's no net force on it to accelerate it. So 11, I'm just going to say pushing a building as an example. Pushing a building, and forces are always equal. Okay. Question 12a, why the cart accelerates when you push it. Sorry, no, question A was why a shopping cart remains at rest if you do not push it. No forces acting on it. Or to be more accurate, the forces are balanced. The net forces acting on it is zero and equals zero. Why did I say that? Because, well, as the trolley is sitting on the floor, on the ground, there's actually weight acting down on it. But then the reaction force from the ground is pushing it up. So those two forces are equal and therefore it's stationary. But there's no forces otherwise in the X plane acting on it. Um, question 12b. Why the cart accelerates when you push it? Well, because now the forces are not in balance. As you exert a force, as you exert a push on it, now you've got a force that is not in balance with the others. So there might be, here's the cart, for example. Okay, here's the cart. There's weight acting down and there's reaction force acting up, and that's it. But if you exert a force of push, of course, it's going to move forward and it's going to start accelerating because there's nothing, well, air resistance is pushing against the cart, but it's insignificant. And question C says, how is the cart's acceleration is related to its mass and how hard you push? As the mass increases, the acceleration is going to decrease because force equals mass times acceleration. That's second law of motion. So as the mass increases, the acceleration is going to decrease, assuming the force stays the same. If you want the acceleration to remain the same, you have to put the force up. If you increase the force, then the acceleration will increase. As long if the trolley's full, right? So if the trolley's empty, you don't have to push as hard to get, say, for example, 1 meter per second. But if the trolley is completely full, then you have to push harder because, well, the mass has gone up. If the mass has gone up, to achieve that acceleration, you have to put the force up. Okay, question 13 says, find a way an astronaut on a spacewalk discovers that his jetpack no longer works, leaving him stranded 50 meters from the spacecraft. If the jetpack is removable, explain how the astronaut can still use it to return to the ship. Well, the simplest way to do this, I'm going to try and rub all of this out. Imagine yourself in outer space and you've gone on a spacewalk and you're about 50 meters away from your spacecraft, which is your lifeline, really. That's where the oxygen and the food and everything else is. That's your way back to Earth. And you find that the jetpack has run out of, I think it's compressed air that they used. So anyway, you suddenly find yourself slightly drifting away or perhaps unable to go back to your spaceship. What do you do? Well, we know from Newton's laws that for every action there's an equal and opposite reaction. So what does that mean? How can I use that? Well, it's simple really. All you have to do as an astronaut, here you are in outer space, and you've got this big heavy bag, and that's you, that's your arms, that's your legs. Okay. All you have to do is get this heavy bag off your back and then you throw it that way. And so once you throw that bag, let me move the bag away. Okay, once you throw that bag that way, what's going to happen to you is you're going to be pushed in the opposite direction towards the spaceship. Simple as that. Imagine it's a lot easier to imagine when you're in a pool. If you're in a pool and you push someone, it just pushes you away. And that's kind of what happens, except you're now in space and there's less acceleration, there's less friction, and therefore things are just ideal. Okay, so that's what happens. You just use the bag to propel yourself in the opposite direction. Number 14 says, analyze, is it possible for an object to move in a direction that is different from the direction of the net force acting on the object? Give an example to support your answer. It's one of those tricky ones. Okay, let's read that one more time. Is it possible for an object to move in a direction that is different from the direction of the net force acting on the object. Give an example to support your answer. So the only example I can think of at the moment is a cannon. Okay, so here is a cannon, and the cannon shoots a cannonball, and the cannonball obviously follows a parabolic motion, and it is experiencing acceleration due to gravity, g, and it's the direction is down. The acceleration, direction of the acceleration, the force acting on it is down. Direction of the net force acting on the object, whilst the direction of the ball or the cannonball is still going forward. So yes, it is possible. Interpret. Figure 5.6 shows a front wheel drive car accelerating from rest. Which of the forces F1 and F2 is the force exerted by the car on the ground, and which is the force exerted by the ground on the car? Okay. Um, Quite simple, really. Think of it as the same example as you would experience in the pool or that astronaut in outer space. If you push an object backwards, you get pushed forward, you get propelled forward. The car is rotating this wheel, in a clockwise position, which means it's actually exerting a backward force on the ground, on the road, in order to be propelled forward. So the question asks, which of the forces F1 or F2 is the force exerted by the car on the ground? It's F1. And which force is exerted by the ground on the car? And that's F2. So F1 is the force exerted by the car on the ground, while F2 is the force exerted by the ground on the car. Okay? And B says, which of the following correctly expresses the relationship between the two forces? Does F2 equal F1? Is F2 equal to negative F1? Or is F2 bigger than F1? Yeah, so if F2 is equal to F1, then they would be exactly equal and not opposite. But we know they are equal and opposite, so it's that one. Now you might be tempted to say, well, actually the car is moving, so F2 is bigger than F1. But remember, the acceleration is different to the force. So the acceleration acting on the object is bigger, but the forces are equal and opposite. So make sure you understand the difference there. Right, question 16 says calculate how much force is required to give a 0.15 kilogram baseball an acceleration of 12 meters per second squared. And once again, we just use our trusty triangle. And here we have force equal, this is number 6.